Hello and welcome back. Coming to you from our offices in the downtown core, amidst a very busy intersection. Today's topic is the empirical rule and its applications. This presentation 3.4 is applications of the empirical rule, standard deviation. We want to illustrate the empirical rule here. We have the frequency distribution here, these rectangular forms, part of a frequency distribution. We've drawn through here what appears to be roughly a normal curve, hump-shaped. On the left here we have the fact that the normal curve seems to occur extensively in a competitive world in adaptation of species. And we're going to look at a case where the mean mu is 70, standard deviation 10. There's the center or mean. If we go one standard deviation to the right, that's plus 10, z equal to 1, and z is the number of standard deviations away from the mean in units of sigma, or 10. And on the left, minus 1 sigma, 60. Now in that region between these two red lines, plus or minus 1 sigma, 60% of the time x will fall, and that gives rise to 34% in each of these regions. If we go another standard deviation, that's another 10, z equal plus 2, z equal minus 2, 95% of the data will fall within 2 standard deviations of the mean. And on the bottom of the screen here we have this notion that the area between these two red lines is the difference between these two numbers here times a half. That's 0.135 on each side. Now we're going to go 3 standard deviations from the mean. 100, 40, and that is 99.7. And coming to the bottom here, this means of course that the region in this here is the difference between 99.7 and 95 times a half, since there's 2 of them, and that is 0.0235. And this is basically the empirical rule. Now, to find the probability x, which is strictly random sample, a random item, less than 70, that is half of this curve, or 50%. Between 50 and 70, we simply add up the 0.135 and 0.34. Between 40 and 80, as you can see here, we're just adding up those numbers. Now let's look at an application. We have the weights of 2 individuals, Tom 85 kilograms, Bob 98, and they're in 2 classifications. We've summarized these on the screen here. So this is your x value. We want to find the z-score, and it's a measure of the deviation that a given point x is from the mean relative to the standard deviation. And here we have it on the screen here. For Tom, here's x, here's the mean, and sigma. Subtract x minus mu over sigma is 3.1. And on the normal curve, we're assuming a normal distribution here. He's at the extreme end here, beyond 99.7% region. Now for Bob, we see here his x, his mean, is 90, standard deviation 8. The difference there suggests sigma, or z, equal to 1. So for Bob, he's actually 1 standard deviation above his mean. So the result is that Tom is more overweight relative to his class than is Bob relative to his class. Now we're going to look at the same data applied to stock pricing. So we have here 2 stocks, and just pause the video at any time and write these down. Here we have a summary. We want to find the z-score of each. We're assuming a normal distribution. Now for stock A, we have x, mu, and sigma given on the screen here, and the z-score is the difference between x and mu relative to standard deviation. So stock A is 3 standard deviations above its mean. very high end. For stock B, the z-score is 1.33, and of course that value is here. And so the question is, if you had to sell, which stock would you sell? And obviously you'd sell stock A because it's way higher, more above its mean than is stock B, and it's more likely stock A will drop compared to stock B. So the answer here would be you'd sell stock A because it's at an extremely high level. Now when the data is not normally distributed, we're saying if it's hump-shaped, if not hump-shaped, it's spread out a great deal, you can't use the empirical rule as such. And we use what's called Chebychevs theorem, which says that within k standard deviations, at least 1 minus 1 over k squared times 100% of the data will fall. So when k equals 2, that's 2 standard deviations that you see illustrated here, the answer becomes 1 minus 1 over 2 squared, or at least 75% of the data will fall in that region. For k equal to 3 standard deviations, we put 3 in there for k, 88.9% of the data will fall within 3 standard deviations. And here we have a comparison. 68, 95, 97. If we know the distribution is normal, if we don't, then we'll fall back to these 3 values here. And note the word at least, which may mean greater than or equal to. Now the criteria for an unreasonable event, and this is where we're going in the course, we have this distribution here with corresponding probabilities for a normal curve. And we're saying anything within 2 standard deviations of the population mean is said to be reasonable. And reasonable denotes a 95% region, if you wish. Anything outside is said to be unreasonable. We've depicted these here. Unreasonable means less than 5% probability. So we're going to look at a distribution of that. Length of pregnancy is normally distributed, mean of 268, standard deviation 15 days, and this woman comes in and finds that the length of pregnancy is 308 days. We're saying what is the z-score? Z-score, x minus mu over sigma, 308 minus 268 over 15, 2.67. And looking at the table here, 2.67, way in the right tail here. As you can see here, this is very, very small. We'll be able to find this from the table of normal probabilities. This is said to be highly unusual or quite unreasonable under the circumstances. Now we're looking at white blood cells. Here's the mean and so on. We've summarized the data here. Computing the z-score, here's mu, sigma, and x. The z-score, 3.77. And on the screen here, 3.77 is way in the far right end here. This is extremely rare event, very unreasonable, and therefore we would probably take action in this case. Well, that's the end of presentation 3.4. We ask you to take notes as required and go to presentation 3.5.